Yeah, I can hear
Sorry
you.
for the interruption, but that's the way life goes sometimes. All right, so this is what I'm going to talk about, and I think I will start off with a little review of what I think we learned last week. Now, Dave is sitting right here in the front row, so he can say, no, you got it all wrong. Excuse me?
Start your presentation.
Oh, I beg your pardon. Thank you. How's that? All right, that's an improvement. All right, so what did we learn last week? An awful lot between Dave Hafmeister and Dave Camp. But I'll go through it briefly. If you have questions, but I think maybe I'll answer some of your questions in the process of going through this. He talked about the causes of the season, and the main effect, remember, is associated with the tilt of the Earth axis, so that in the summertime in the northern hemisphere, not only are the days longer, but the sun comes in at a higher angle, and its energy is not spread out so much. What controls the Earth's average temperature? It really comes down to what we call energy balance. Energy comes in from sunlight, and it's sent out by infrared radiation from the Earth's surface. And if more comes in than goes out, the Earth is going to warm up. There's just no getting around that. That's about as basic physics as you can get. Then he talked about the greenhouse effect, and I think this phrase, the planet's insulating blanket, says it all. It intercepts some of this outgoing infrared radiation, and some of that, instead of going straight out into space, is sent back to the Earth's surface, and that warms it even further. And in fact, had it not been for the Earth's atmosphere and these greenhouse gases, the Earth's surface would be about 0 degrees Fahrenheit. Then we talked a little bit about past climates and evidence for the connection between the amount of carbon dioxide, a powerful greenhouse gas, and the Earth's temperature. And Dave Camp showed you over vast stretches of time how there was a close connection between the carbon dioxide composition in the atmosphere and what the average temperature of the Earth was. Whenever I say that, people who give me a hard time say, yeah, but just because there's a correlation, that doesn't mean there's a cause or a connection. So we'll talk a little bit about, in each case, what is cause and what is effect. And then Dave Camp emphasized that there are vast differences in what he called time scales affecting our climate. The longest one is the slow brightening of the sun itself. When I was a graduate student, the very first paper I ever published was a computer model showing how the sun changed with time as it uses up the hydrogen in its center and converts it into helium. And then we have much more rapid effects going on right now, some of them caused by what humans are doing to change the composition of our atmosphere. Well, what is the source of the recent carbon dioxide rise and the resulting increase in the Earth's temperature? And Dave showed some evidence for that. One of the striking things was that as you burn fossil fuels, they combine, the carbon combines with the oxygen in the air, and so as the carbon dioxide is going up, you can actually see some of the oxygen in the atmosphere decreasing. That's one strong indication of it. But you can also just look and see how much fossil fuel humans have burned in the last 100 years. And you can calculate how much carbon dioxide that is given off. And in fact, that more than accounts for the actual measured increase in the carbon dioxide, because the ocean is absorbed a little bit more than it used to because of this increased concentration of carbon dioxide. Then Dave Camp talked about feedbacks, and these are processes which amplify things which would normally cause an increase in the energy flow into the earth. For example, suppose the sun got brighter. And we know the sun changes a little bit over the year with the sunspot cycle. And there are other effects which tend to add to that or subtract from it, or at least oppose it. Another effect, of course, is the increased trapping from the increased carbon dioxide. There are secondary effects which may amplify that warming or oppose it. And two of the most important are the increase in water vapor, because as the atmosphere and oceans warm, that allows more water vapor to exist in the form of vapor rather than condense out as rain. And water vapor is itself a strong greenhouse gas. Now some people say, well, does that mean we have to stop watering our lawns because we'll cause global warming? No, that's a feedback, and the water vapor adjusts to the warming that's initiated by other processes. And then we talked about the albedo feedback, and I know people said, what's albedo? What's albedo? Well, albedo is simply a measure of the reflectivity of a surface. So it's defined to be the percentage of sunlight that's reflected back into space. And so, for example, fresh snow has a high albedo. It can be as high as 90%. It's a very shiny, reflective surface. Whereas ocean water, open ocean water, will absorb quite a bit of sunlight. And that's why this albedo effect is a positive feedback. What that means is, if there's some warming and the ice or the snow, which used to reflect a lot of sunlight, disappears and is replaced by dark ocean, then even more sunlight is absorbed. That causes further warming. That causes further melting. That causes further absorption of sunlight. And so that's a positive feedback. Then the very important distinction between weather and climate is something which people simply cannot get through their heads at some time, and they'll say, well, last year it was cold, or this year it was rainy, or whatever. You need to take long-term averages to really understand what's going on in the climate system. That's an important distinction because people often neglect that. I like to think of it in terms of someone trying to lose a little weight, as so many of us do. And you say, gosh, I'm going to try and lay off that peanut butter, but you just can't resist it sometime, and you mainline some of the peanut butter, and then you get on the scale, and lo and behold, you actually lost a pound that day. And you thought, oh, that's all hogwash. I don't need to worry about eating peanut butter. But you need to weigh yourself every single day for a long period of time to really see if you're making any progress. So that's the distinction between weather and climate. And then finally, computer models try and incorporate what is going on in the climate. And I need to emphasize very strongly, climate models are not weather forecasts. What they're trying to do is project statistical averages over what's going to happen. They're not going to tell you whether it's going to rain on February 17th, 2027. But I know that some of you took my course last year, and do you recall the little chicken feather experiment that I did? I had a fan up here, and I had a chicken feather, and if you drop the chicken feather about 3 inches from the table, you can predict where it's going to land pretty accurately. That's a short-term weather forecast. If I held the feather up here and let it go through that fan, it went all over the place. It would be impossible to predict where that feather was going to land. I drop another one almost exactly the same way, and it will fly off in some completely different spot. Then I had this whole bucket full of chicken feathers, and I dumped them out all at once, and lo and behold, it made a nice pattern on the floor, and you could then talk about probabilities of where those feathers would land. And that's what climate models do. They talk about probabilities of what's going to happen in the future, depending upon what we do with our atmospheres. Okay, so now I'm going to go through this quite quickly because John already showed several of the physical impacts of a warming world, and I'll just run through them quickly. You'll recognize a couple of the plots that John showed. This is, in fact, just the raw global air temperature that people have tried to reconstruct. And remember, this is global. That means you'd like to be able to measure the temperature above every square mile of the Earth's surface, not just one spot here, one spot there. That's not so easy to do because we don't have parts of the world in the far north and the far south covered with weather stations. We have lots of them in the United States. So it takes some sophistication to try and reconstruct what the global temperature was through the years, and several groups have done this. There are actually 5 different groups in this plot. You can see they all agree quite well. Let me just ask you, look at this. I was wondering about this. What do you suppose happened here about 1878 or 1879? Volcanic eruption would actually cause a cooling, because what the eruptions do is to throw out reflective particles, and you can actually see cooling from some of the more intense volcanic eruptions. This turns out to be a really strong El Nino event, and it had some profound and unfortunate circumstances. So we do associate El Nino episodes with warming and La Nina episodes with cooling. And as John mentioned, we've had more La Niños lately than we have El Niños. So you can see, though, however you slice it, that the surface temperature has increased. Not uniformly, not by any means. A pause here during the 1950s to 70s. I'll talk a little bit about that. And then beginning again, a fairly steep rise. But that's not, and this is a more detailed look at it, and I'll come back to that in a moment. But there are many other indicators which have nothing to do with thermometer measurements. These are 2 pictures of glacier in Bolivia, and you can see the effect of warmer temperatures. And then John showed this picture of the Muir Glacier in Alaska, and you can say, well, cherry picking, you guys just picked the only 2 glaciers in the world which are doing this. Not so. There are institutes which measure glaciers throughout the world, and while not every single glacier is retreating, on average they are. They're getting thinner and thinner and having less and less volume of ice in them. And this is a graph which shows you the amount of ice in all the glaciers in the world, the representative ones, versus time. And you can see it's going down, 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 and in fact starting to accelerate. And this is very characteristic of what we're seeing. Things are accelerating. The rapidity of the changes we're seeing is increasing. This is the huge ice sheet on Greenland, and John mentioned that it is starting to shed ice into the ocean. People say melting. It isn't really so much that it's melting, but the warming oceans are allowing these huge tongues of ice to slide into the ocean, and that's contributing to sea level rise. John mentioned there were 2 effects. The warming of the ocean is perhaps 2/3 of it, and the melting or the sliding of the ice caps in West Antarctica and Greenland are contributing about the rest. And you can see that this effect, too, has been accelerating. This is measuring the amount of ice in Greenland, Antarctica, and this is the combined effect. And once again, see in over just the last 20 years or so that the shedding of ice has increased. This is the snow cover in the northern hemisphere in June, and it too has been decreasing on the average more and more and more. John showed you the amount of summer ice decrease Actually, I want to make it clear that what he showed you was the area of the ice, but the same thing is happening in terms of the total volume of the ice. And he showed you this graph. Now, he stopped in 2012, and people will say, oh, well, yes, but it's recovered. You've heard that before. Yes, it has recovered. This is what it was in 2013, but this is not my idea of recovery. I would say it's continuing to decrease on the average with years. And again, you can say, oh, well, who cares about the last 30 or 35 years? Let's look at the longer term history. And this is an attempt to reproduce what's happened to the Arctic sea ice over the last, well, 140 years. And you see, once again, a dramatic decrease in the amount of ice at the Arctic. And this is the decrease in the volume of the Arctic sea ice. So there are many, many effects like this. I would, if I had the time, well, what the heck, let's see if I can do it. This is so cool because it's the preview of what I want to talk about next, if the sound works. Can you hear that? Well, no. Yeah, let's see if we can find it. Okay, good. Thank you. Okay, I've done this. That's no trick. It really happens. Now, the consequence of this is that most, as he said, most of this energy imbalance goes into heating up the ocean. But because the heat capacity is so large, even though a huge amount of energy is being stored up there, the temperature isn't really, really rising all that much, but it will come back to bite us eventually. Not particularly. It would be a small effect. I think maybe he was stretching it out a little. But that's right. If you heat the water in the ocean, it will expand, and that expansion, coupled with dumping some of the ice into the ocean from Greenland and West Antarctica, is what's causing the sea level rise. I'll show that again. But you can see this graph here, the blue line, shows you how much energy the ocean has been gaining compared with the small amount on the land, atmosphere, and the ice over the years, about the last 50 years. This is a tremendous increase in energy. When I calculated that if you wanted to account for the same amount of energy increase, you would have to take one of the reactors at Diablo Canyon and multiply that by about 200,000 to generate the same rate of energy input that's happening in our climate. Yes? I'll talk about some of these changes in slope in a moment. The heating is not entirely uniform, and I'll comment a little bit more about that in just a moment. Okay, but I wanted to emphasize that that is the big heat bucket for our climate system. And this is another graph showing the same thing, the amount of energy that's going into the ocean. And what I want to emphasize is that it hasn't stopped. It hasn't slowed down. If anything, it's increasing. This is a plot of energy content of the ocean versus time. And John showed you this consequent rise in sea level of the entire average ocean, with a marvelous set of satellites that have extreme accuracy in measuring this. Now, I'm not going to explain what this graph is, because this is really something that Lou Patelka will talk about, but it really measures what's happening with the flora and the fauna as the things that birds and bees like to do, and flowers and trees, is moving earlier and earlier, a few days in earlier and earlier spring. But what I like to say is that even though some people don't acknowledge that the Earth is warming, they're not as smart as the birds and the bees. They know this all, and they can already see what's happening. Now, when you put this all together, here's my take on it. Individually, you might say, well, none of these are entirely convincing. But when you take them all together, you have this, and 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 I would say that reasonable people would conclude not just that it's pretty strong, but the evidence for a warming world over the past many decades is overwhelming and unequivocal, and that's the word that people in scientific community use. Now I'm going to take just a couple of more minutes to say, okay, but what's caused that? Where did all that energy come from? Well, one thing that people point to is, well, maybe it was the sun. But in fact, the sun has not been increasing in brightness. This looks like a large change in energy output from the sun, but the scale is such that this is only 1/10 of 1%, and there has been no increase in the time over which we can measure it accurately. So no, it wasn't the sun. It's the increased trapping of heat from carbon dioxide. I'm just going to mention a couple of the most common misunderstandings in the last 5 minutes here, because I hear them all the time, and you will hear them too. The danger in me doing this is that people say, when you talk about these, people remember these as if they were true. These are not true. These are misunderstandings. I won't say myths. I'll be nice and say misunderstandings. The one you will hear most commonly nowadays is that carbon dioxide continues to go up, but there's been no warming since 1998. So what the heck are you talking about? Well, here's in fact the prime example of what people do when they tell you that. And you talk about cherry picking. Boy, this is the ripest cherry of all. I think if anyone in a high school statistics class were to do this and say, well, look, here was 1998, and by golly, here's 2012, and there's been no warming. So what do you think of that? Well, the simple-minded statistical analysis would involve something that high school students learn, I think, in statistics classes. It's called least squares, and you fit the best line you can to all this data. And in fact, it is true that recently there has been not as much warming. The rate of warming has slowed, but it certainly hasn't stopped. But by far the more important point is that the energy has been going into the ocean. What's caused that recently? And the explanation seems to be that because of the predominance of La Niñas over El Niños, most of the heat is getting mixed in to the deeper layers of the ocean. I don't know if you can see this faint blue line here very well, but this is just the top surface layers of the ocean, and of course that's coupled closely with the atmosphere. That heat has not increased particularly, but as I showed in the previous slide, the total amount of energy has. And so that's one of the main contributing factors. The second most common thing that I hear is that, oh, isn't this just all part of a natural cycle? Climate's always changed before it. Yes, it has, but the rapidity with which it is changing now is unprecedented. These past cycles, which Dave Camp showed about, the ice ages, they took tens of thousands of years because of these changes in the Earth's orbit. And this is an example of something which is a natural cycle. This is not a natural cycle. And if you think that somehow the Earth suddenly decided to increase its carbon dioxide just because it felt like it, well, you're entitled to your opinion, but I do not share it, nor do I think any other climate scientists share it either. This is a graph of the amount of carbon dioxide over the last 10,000 years deduced from ice core data, and you can see that it is shot up like a rocket. Put this in the context of what has happened for the last several 100,000 years, and you can see that we're doing something that's never before happened, as far as I know, with this rapidity in the entire history of the Earth's climate. And that's why people are concerned. There is a famous saying, or a quotation, from one of the very earliest people who called attention to this problem, that we humans are conducting an uncontrolled experiment on the climate system by profoundly changing an important constituent of the Earth's atmosphere. So I think I'll stop there because it's now 11 o'clock. I showed you some of the other misconceptions. If you want to ask me about them later on privately, or if we have time at the end of the second hour, I can talk about those as well. But let's take a break. Is Pete Schwartz, I don't think, is here. Oh, he is. Great. So, Pete, well, why don't you just do your thing now. Tell them about this resource.
Good morning, everybody. Hi, I'm Pete. I'm in the physics department at Cal Poly. And
Just talk into it. Yeah,
do I need that microphone?
Yes,
Ah, right. With the microphone now. Most of my interest, what I teach, what I do research on, is energy, society, and the environment, and also development. Like, how do we address the other 3/4 of the planet that we think the standard of living is going to improve, or we'd like to see that, depending on who we are. But what I want to tell you about is, for the energy, society, and the environment class that I teach, I've assembled about 40 or 50 videos on YouTube that I'd like to extend as a resource. So, like, if you want to know what is fracking, or what is some of the science or societal issues involved with nuclear. I have a, well, let me show you. I want to show you how to get those resources. So can I hook up to this?
You can, but it'll take you. I'll tell you what. Let's take the break now, and then you could be hooking up during the break.
That's fine.
And then you can do it before you start. Okay. So we're going to be taking a break for 10 minutes. Try and be back, please, at shortly after 10 after 11.